Hi, so welcome to the last of the L function lectures before we all arrive on campus. And so what I want to do today is just, keep it open for questions of, things that you've read. Hopefully by now you've had a chance to look at the various papers, some of the talks and whatnot. And the goal is not to have everything mastered completely, but rather to have a sense of what the subjects are, what the kind of questions are, and to, talk a little bit about what you might be looking at. So if people have specific questions, I'm happy to talk about them. If not, what I will probably do is go to some of the slides and just talk about the paper there. So are there any questions? Okay.
Oh, I have a question, which is kind of more meta than math. So for this summer, you said in one of your emails that we're extending one of your papers or co-authored papers.
Yes.
On symmetry types of like modular form L functions, right?
Yes.
So how much like modular forms like will we need to like know for that? Like, should we be studying on that, or is that something where
we should be able to use it completely as a black box?
Okay, because yeah, I saw that like in that paper there was some stuff with like some kind of sums, I think. There's like some technical stuff, but then also like once that was done, it was kind of like a separate thing. Okay, but so it's just a black box, like where
exactly. And so what I might do, did we talk about Dirichle L functions last time? So if not, let me talk about Dirichle L functions quickly. And this will give you a little bit of a sense of what's going on. So this is the simplest possible case. So normally you use P as a prime, but since we are going to be having multiple things that are prime, we need another letter, so we'll use M. So it makes things a little bit easier if M is a prime, but it doesn't have to be that way. One of the big questions you can always do in the subjects is how general can you make your arguments? What is a technical convenience and what is absolutely essential? For many things, we can easily go from prime to square free, but going beyond square free is actually quite hard. And there's a paper I did with a couple of students, all from liberal arts colleges. No one had ever done modular forms with a generalized Iwaniec-luo-Samak to the non-square free case. And it was really painful. I was much happier to be the mentor than the mentee for that project. But there was no real obstruction. For other things, for cuspidal new forms, if you leave being square free, you no longer have an easy way to distinguish which forms have even and which forms have odd functional equation. So it's not just a technical challenge, it's just we don't have the same machinery available. So you always want to get a sense of what kind of results do we need and why. So here, M is going to be a prime, but that's just for convenience. And we're going to look at what's called characters. So Z mod MZ star, so these are the numbers 1, 2, 3, all the way to M minus 1. And we do this with clock arithmetic. So if we are looking at a clock with 7 hours, then 3 times 4 would be 12, which would be the same as 5. And so we can define a function on the numbers, Z mod MZ star as follows. So we're going to let zeta of M minus 1 be an M minus first, essentially root of unity. So if we raise this to the M minus first power, we get 1. And the simplest character to define is the principal character, which sends everything to 1 that is relatively prime to M, and sends anything that shares a common factor with M to 0. Well, if M is a prime number, this isn't too bad. The only things that we have to worry about are 0M, 2M, 3M, and so on. But more generally, we could do this for a composite M. That's the principal character, and it's pretty easy to understand. But there are other characters we can define. And again, our characters are going to be maps from the group Z mod MZ star to the complex numbers, actually to the complex numbers of absolute value 1, except for the numbers we send to 0. So you're either going to have absolute value 1 or 0. And what we do is, given some number g, g is going to be a, often might be a generator of the group. So it's a beautiful theorem that when m is prime, this group is cyclic. And we're going to just send it to a power of the primitive m minus first root. And it turns out that for any choice of L between 1 and m minus 2, this is going to give us a nice well-defined map. And the effect of chi on a product, your G1 times G2, your two elements of this group, is just going to be the product of chi G1, chi G2. So if you've done some abstract algebra, you might recognize maps like this. It is unusual to be able to write things down as explicitly as this. And again, if you haven't seen calculations like this, don't worry. I will do, if people want a slower, more detailed lecture. What I want you to get from this slide is I can write down everything explicitly. This is just a really nice exponential function. I have a group here where I can write the elements as powers of a generator. It's an interesting question to find out what is that generator. And I can write down all these maps very explicitly. We can't always do that, but when we can, it makes the calculations a lot easier. And then we define a Gauss sum as follows. So we take k ranging from 0 to m minus 1, and we look at, for fixed character chi, we look chi of k times e to the 2 pi I k over m. And it turns out that this number is going to have absolute value square root of m. The interesting question is figuring out what is the sign. And that was a very famous problem which Gauss was very proud of solving. And we can use this to build up an L function. So we see in previous lectures the Riemann zeta function, the sum of 1 minus p to the minus s inverse. All that we do is we replace the chi of p here. So if you think about it, if we take chi of p, if we take chi to be the principal character, then the only time the principal character is 0 is if the prime happens to be m. Every other time it's going to just be 1. So this would be essentially the Riemann zeta function, except for a trivial modification, which is easily understood. So what happens with the principal character is pretty much standard. The non-principal characters behave far more interestingly, because now we're going to get some real cancellation going on. And it turns out we have a functional equation very similar to the Riemann zeta function. And it's just a matter of doing a little bit of work to figure out what all the different factors are. And so we have a nice equation like this. There is the explicit formula as before, where we can look at the scaled zeros of this L function, and we get the following. So sums over the scaled zeros of our test function phi is equal to sums of phi hat at the primes. And now we have multiplying by the coefficients of the L function, the chi and the chi squared, and your chi bar is just the complex conjugate. Now you might notice that we only have sums over primes, and these are really sums over prime squareds, because chi of p squared is just chi of p, or chi squared of p. The reason we don't worry about the other terms is they're going to be lower order. Notice that here we have a p to the minus a half, p to the minus 1. The next is going to be of size p to the minus 3 halves, then p to the minus 2, then p to the minus 5 halves. And with a little bit of work, you can show that all of those terms contribute 0 in the limit. So what we now have to do is understand these two sums here. And I'm not going to go through the details because that's in the notes, that's in the video that you can watch. But essentially what happens is we have these orthogonality relations. We have formulas for summing. If you fix a k and sum over all the characters, we have a result for what that equals. And then, well, if we don't have the principal character, we can easily remove its contribution, not a big deal. And then we just substitute that into our expression. And when the dust settles, we just have a bunch of sums. And without too much trouble, we can show if the support is sufficiently small. So remember, phi hat vanishes outside the interval minus sigma sigma. Well, what does that mean? Well, forget about the pi. M is going to be our parameter going to infinity. So basically, p can get up to m to the sigma. So as long as p is a little bit less than m to the sigma, the argument inside here is essentially going to be at most sigma, so it's going to be non-zero. If, however, p is greater than m to the sigma, then we're going to be evaluating phi hat beyond its range, and it will trivially be 0. So we can get that there's no contribution from these terms in these ranges. And so what you can see here is the explicit formula is very valuable in converting sums over zeros to sums over primes, but then we put in some number theory to figure out the corresponding sums. What I want to do now is I want to switch, and is it now showing results from Iwaniec-luo-Samak? Is everyone able to see that?
Yep.
Okay, so I want to switch to the main family that I want to study. So I want to talk about the seminal paper by ILS, where they looked at the one-level density for even weight K cuspidal new forms of square free level. And as I remarked earlier, the square freeness is very important if you want to split by the sign of the functional equation. If you want to amalgamate everything, then you don't have to worry about being square free. And they looked at some other families as well. I'm not going to really concern myself right now with that. Here is a real blitzkrieg overview of what we need. Essentially, we're looking for generalizations of periodic functions. So can anybody give me one of their favorite periodic functions?
Sine.
Sine, right? Sine, cosine, these are wonderful functions. And so what we have here is a function that's a little bit different. So we can have matrices act on complex numbers as follows. So if you have a matrix A, B, C, D, and you act on some number Z, you would write this as AZ plus B over CZ plus D. So this is a very well understood mapping. Given a complex number with imaginary part positive, gamma of Z will also have imaginary part positive under such restrictions. And so we have a nice map from the upper half plane to the upper half plane. If I choose my matrix to be 1, 1, 0, 1, so basically the identity matrix over here, a 1 up here and a 0 down here, that just sends Z to Z plus 1. That's the same as translation. Oh, that's the sines and the cosines we know about. And so what we're doing here is we're actually looking at a generalization of these trigonometric functions. And it turns out that these functions have a lot of wonderful properties. They occur in a lot of really good mathematics. We can write down a Fourier expansion. This looks very similar to the L function. The only thing that we're really changing is rather than having, there's a little typo over here. What's missing over here?
You want an n in the exponent?
Yeah, there should be an n in the exponent. So how do you know that I made a mistake? You have to know I'm wrong.
Well, the sum doesn't depend on n. Well, at least the exponent doesn't.
Yeah, this part over here wouldn't depend on n, and I could just pull it out. And so looking at this, that there has to be a mistake. Years ago, for one of the small projects, we were looking at a paper, and it had an integral of an odd function over a symmetric interval. What is the integral of an odd function from -2 to 2, for instance?
0.
0.
Yeah. So we knew there had to be a mistake somewhere. There's no way you would keep something like that. And so, I thought they forgot to put in a factor of x somewhere. But it took us a while to convince ourselves that that really was the mistake that was made. We knew what was written had to be wrong. And then one of the great problems you have in the subject is how do you want to normalize your coefficients? If I have an L function, if I multiply it by 17, it's still an L function. So there's two natural definitions. We can define what's called the Petersson norm. So if I give you two L functions, their dot product is the integral of f times g bar. And instead of just integrating over the entire fundamental domain, this is a region in the upper half plane, we put this extra factor of y to the k minus 2. It's just going to make things transform nicely. And again, right now, this is really high-level overview. If we start working on these projects, I'll get into a little bit more of the nuts and the bolts, but I want to give you a sense of where things are going. So one possibility is we can normalize our functions so that they have Petersson norm 1, or we can normalize them so that they have first coefficient 1. Does it make a difference? Should it matter which normalization we use?
No, but maybe you could facilitate the computation because we said
Exactly.
look at just the first two terms, maybe.
Yes. And so it's a lot easier to have the first term be 1, then you get that the coefficients are multiplicative. And so it's just a little bit more convenient to do it that way. If you remember your multivariable calculus where you might find lengths of curves, it's very convenient if you parameterize them by unit speed, because then you don't have to worry about, oh crap, do I have to divide by something related to how fast I'm traveling? Well, if you're always traveling at 1 unit per second, then it doesn't matter if you divide by it or not. And so
Right, you said that you want to normalize the coefficients because then they'll be multiplicative. Does that mean that like a of sub mn equals a sub m times a sub n?
if m and n are relatively prime, yes.
And that's from the L function expansion, right?
And that's in the L function expansion. But if you normalize them differently, then you're going to have other factors coming into play. If you look at this normalization over here, we're dividing by the norm of the function, the gamma function, and then a power of n. These are all well-defined things, so this normalization isn't too bad. And then the big result is that if we have an orthonormal basis for the weight k level n forms, if we want to study a sum over basis elements of CFN, C bar f of n, where f is ranging over my basis and m and n are 2 numbers, then we have a beautiful result where if m equals n, we get a +1. Well, that kind of makes sense. If m equals n, these 2 numbers are complex conjugates, so it's just the length of that. And it's not surprising that maybe I've defined this so it's going to normalize to 1. And then we have this massive term over here, which involves a Bessel function, which we'll talk about shortly, and a Kloosterman sum. Oops. Oh, in the wrong way. Now, if you've never seen a Bessel function before, not a big deal. It's extremely well studied. There are huge, huge volumes written on its properties. Same thing for the Kloosterman sum. And what's nice now is at this point, the number theory has shifted from the modular forms to these nice functions and their resultant sums. So at this point, because I've averaged over the family, I no longer need to know things about those modular forms. And this is what I mean about being able to use certain results as a black box, where it's wonderful if we knew all the details as to why the Petersson formula is true. But it turns out that we can just use it and jump from a sum like this to a new sum like this. So again, the purpose of today is to just give a high-level sense of how we're going to go about things. And again, please feel free to stop me at any time with questions or comments. So now, we start putting things in. We have a sum over scaled zeros. We get things on the right-hand side. As I was remarking, we have our multiplicative properties. And then the big result is that for a new form of level n, we have the sign of the functional equation is the following. And it's essential here that n is square free. So, mu of n is a nice well-defined quantity. Lambda f of n is the Fourier coefficient. I, that's fixed. Root n is fixed. So basically, if we know lambda f of n, we know the sign and vice versa. And this allows us to very easily split sums by the sign of the functional equation. We just look at 1 plus epsilon f. And if we do that, it's going to be 2 whenever we have an even form and 0 otherwise. And if we look at 1 minus epsilon f, that will be 2 whenever we have an odd form and 0 otherwise. And so we can, at the cost of introducing another value of one of these into our expression, we can actually adjust the sum to be over just the forms with even or just the forms with odd sign. And again, if you're not following all the details, that's fine. This is high level. We can actually do the split.
Sorry, is mu there? Is that the Mobius function, or is that some other function you've introduced?
I believe that's the Mobius function.
Okay. I didn't miss anything.
I'm pretty sure it is the Mobius function.
I was just wondering if there's like some other function I might have missed, but
No,
I think
I'm
it
pretty
doesn't
sure.
really matter. But
There is another function, mu of n, which comes into play as a related volume, but I am pretty sure here mu is the Mobius. The key thing is it's a nice, well-defined function that is going to be very easy for us. And this is not going to depend on the form. It's going to just be something that's fixed. So again, a lot of these times you want to play the game, where's the dependency? And the dependency here is just on this one part, the lambda f of n. And so this is the big result from Iwaniec-luo-Samak. So the first is we have a Ramanujan sum. If you see Ramanujan's name attached to something, probably a good thing to look at. Lots of wonderful properties about Ramanujan sums. And it's basically summing e to the 2 pi I a n over q, where a runs over the invertible elements mod q. That's what the star means. And what Iwaniec-luo-Samak showed is that essentially when you look at that Bessel-Kloosterman term, when you do a little bit of work, it expands out to looking like this monster over here, which can then be evaluated to closed form as a nice integral of your test function c against a nice density function, the sine 2 pi x over 2 pi x with a few other things, plus a smaller correction term. I don't really want to go into all the details about all the stuff over here. You know, a lot of this stuff is not needed if, for instance, you just assume n is maybe a large prime, and it's a question of, you know, how general do you want to prove things? This is a really good philosophy question. When you are proving things for the first time, it's often a good idea to do, you know, the simplest case you can, so you're not drowning in notation and you're not dealing with too many things. Try to do the simple case, get a sense of what's going on, and then see how far can you push it. How hard is it to go from n is prime to n is square free? And we actually see it's really not a huge deal. It's a little bit more bookkeeping, but it's not a big deal. To go from n square free to general n, that's a tremendous amount of work. And it was, you know, a wonderful job by those students, you know, a few summers ago, that they were the first people to actually push forward and do that calculation. Unfortunately, because we don't have the generalization of the sign of the functional equation, they weren't able to go all the way and split by the sign. They could only do the full family. Okay, so roughly what goes on is mathematicians are lazy. As much as possible, we try to do as little work as possible. And so the idea is, what if we just crudely estimate things? Is that enough to make the calculation work? And so here is a interesting question. Can you prove that, how many people know Dirichle theorem for primes in arithmetic progression? Okay, Scribe, would you like to say what that is?
It just says that there are, for any number m, there are infinitely many primes mod a, where a is relatively prime, to m.
Excellent. So if the GCD of AM equals 1, then there exist infinitely many primes P congruent to A mod n. And in fact, more is true. If we call the number pi AM of x is the number up to x, then this is, to first order, it's pi of x over phi of m. And here, pi of x is the number of primes less than equal to x. And phi of m is the number of integers relatively prime to m. So it says to first order, the primes fall evenly in all the different congruence classes. So here's my question. Prove, if possible, that pi of AM over x goes to 0. So can you just prove elementarily that each arithmetic progression has 0% of the natural numbers up to x in the limit. Any thoughts?
Can you just approximate pi of x by log x?
So if you're willing to use pi of x is x over log x,
Okay.
then pi am of x is less than or equal to x over log x, and done. So as long as you can get some kind of elementary bound on pi of x, you win. And so if you've heard of Chebyshev, I have been arguing for years that we should spell his name differently depending on which one of his theorems we want to quote. But Chebyshev proved there exists 0 less than a less than 1 less than b, such that for all x greater than or equal to some x naught, we have a x over log x less than or equal to pi of x less than or equal to b x over log x. And so that would be enough to prove a result like this elementarily. It would give us a bound of pi of x that's sufficient to prove something like this. So as a general rule, mathematicians are lazy. We try to do the simplest calculation possible without doing much work. And so years ago, I actually gave a number theory test where I asked the students to prove that there were infinitely many composites in arithmetic progression. And I might have even asked them to talk a little bit about the density. And if you know results about how many primes there are, it becomes trivial to talk about how many composites we have. What this is doing over here, the limited support sigma less than 1, is just saying, if we put in some trivial estimates, can we evaluate the contribution of the terms that arise when we look at these expansions over here, these sums of the lambda f of p's? And the answer is yes. If we assume that sigma is less than 1, here's what the Kloosterman sum is. We can trivially bound it. There's lots of different bounds on the Bessel function. And when we put all these together, everything works out. Then the question becomes, what if you want to do larger support? Well, if you have larger support, then you have more complicated terms. And with a little bit of work, you can get up to -2 too. And then we want to try to increase the support. I'm not going to go through all this. I think there's a video for this as well. Is that correct? Does this have a video? Or just, yeah, this has a video, yes, excellent. So I'm not going to go through all the details here. This is the main part I want to go through, is we do a little prep work, and the goal as much as possible is to remove all the modular forms and get nice number theory things to sum involving just elementary functions like the Euler-Toscan function, Dirichle characters, and stuff like that. Anybody want to guess when this calculation was done? So if you look at the slide, you should be able to figure out when the calculation was done. What year?
2006.
Almost, 2005. We were expecting that it would be published and in print in 2006. 2006 is a good guess. Why do you think we're using a number like 2006?
It's arbitrary.
It's arbitrary. This is to just show the reader it does not matter. We just need some big number. And you could argue, well, what's the smallest power that you need to make it work? For a calculation like this, it's not necessary. And so it's often an interesting question as to how general do you want to prove something? A couple of years ago, I was asked to referee a paper by a recent PhD student because he was quoting a theorem in one of my papers. And I laughed because the theorem that he quoted, which was for me, was actually me quoting the theorem from his PhD thesis, where he just calculated the main term and I needed the first lower order term. So I just did a few extra steps and calculated it and attributed it to him. I'm not trying to steal his result. but I ended up getting his paper to review because I had the result. And the question is, when you're writing things up, how much generality should you go for? The more general the result, the more useful it's going to be, but the more complicated the proof. And so a lot of times we actually choose to prove not the most general thing we could, but something that is sufficiently general to be of use. And then if somebody wants to generalize it and push it further, it's often very clear what to do. So again, our goal is to try to see how to push things and eliminate as much as possible the advanced modular forms and move into the subject of combinatorics and elementary number theory. And again, elementary does not mean easy, it means just using the more basic functions. And so here is the expression that we end up getting. We have our two test functions. Here we chose them to be the same. Phi, the first one, phi of the second one. We have a Bessel function now with two parameters. And then we have a dx1, dx2 over the square root of x1, x2. And this is the double integral we need to do. This double integral is the generalization of this integral over here. It should look very similar to the integral piece over here. And then we would just hit it with all this garbage over here and do all the sums. So what one word do we use to describe mathematicians?
Lazy.
Lazy. Mathematicians are lazy. We have this beautiful result by Iwaniec-luo-Samak where they did the one-level calculation. So this is a project I've thought about giving people for years. If people are interested, it's probably worth doing. What if we try to actually just calculate this damn integral directly, and just try to generalize the Iwaniec-luo-Samak argument from one dimension to two dimension? What I did instead is I cheated. I introduced the following change of variables. Let's let u2 be x1, x2, u1 be x1. So x2 is u1 over u2, x1 is u1, and then the Jacobian of the change of variable. Hopefully this is vaguely familiar. In polar coordinates, this is the rd theta. Anybody want to tell me what the change of variable volume element is for spherical? Anybody remember?
Rho sine one of the angles, I think.
Excellent. And so it's rho squared because the angles don't have a length. And so you've got to d rho, d theta, d phi. So you need two rhos. And depending on whether or not you're a mathematician or a physicist, you say sine of phi or sine of theta. The physicists have theta coming down from the z-axis. The mathematicians have phi coming down. And it's supposed to be this sine of the angle coming down from the z-axis. So the Jacobian just tells you how to change an element, dx1, dx2 to du1, du2. And when we plug things in here and we do our change of variables, we get phi hat log of u1, phi hat log of u2 over u1. And now the nice thing is the Bessel function is evaluated just at one function, at u2. We have a du1, du2 over u1. Okay, that's much better. Does anybody see anything nice about the function's phi?
You can split up the logarithm.
Yes. So whenever you see a product or a quotient, you should always be thinking logarithms. The log of a product is the sum of the logs. The log of a quotient is the difference of the logs. So when I do that, I then get, if I let log u1 over log of RBW, I get phi hat of w1, and then phi hat log u2 over log of r minus w1. And if you've done some probability, you might notice that this is just a convolution. It's basically the density for the sum of two independent random variables. This is a very well understood operation. What matters to us is that this gives us a new function just of u2. So at this point over here, I can just execute the u1 integral by itself. And when I execute the u1 integral by itself, I've changed variables so now it's a w1 integral. It just gives me a new function. And let's call that function psi of 2. And so now, when I substitute, I now get the following. Does this remind you of anything? So does this look like anything we've seen?
The one level calculation?
Yeah, if we go back to what Iwaniec-luo-Samak did, it looks very much like what they had over here. So we can now use the Iwaniec-luo-Samak result and just plug that in. Not surprisingly, if we had the 3-level density, we would do our change of variables would be x1, x2, x3, x1, x2, x1, and it would just proceed very similarly. The problem is when we do this, the resulting calculation we get does not look like what random matrix theory was expecting. Random matrix theory was expecting us to do the 2 or 3-dimensional integral, and we didn't. We changed variables and we did a 1-dimensional integral instead. And so the annoying thing is at the end of the day, we have 2 expressions that we believe are equal, but we don't know that they're equal. And so I will give one of my favorite examples. Let's see, there's so many great things. So Pascal's identity. So n plus 1 choose k plus 1 is n choose k plus n choose k plus 1. Right. I am assuming everyone has seen this. If you haven't seen it, just pretend that you've seen it. Anybody know how to prove this?
You can prove it with the definitions, I think.
So one is proof, brute force multiplication. If you just put everything in and just multiply things out, you've got it. You could do a proof by induction. Look at, say, x plus y to the n plus 1 is x plus y to the n times x plus y. My favorite is proof by story. So I need 2 objects, two collections, one that you like and one that you don't like. Anybody want to volunteer?
Chocolate bars and broccoli.
Okay, chocolate and broccoli. Okay, so imagine we need k plus 1 items, and we have n chocolate and 1 piece of broccoli. Oops, I'm sorry, it's not n plus 1 that we need. No, sorry, we need k plus 1 items. Good, I would have corrected. So what I can do is I have n plus 1 objects and I need to choose k plus 1. So that's the number of ways I can choose k plus 1 objects from n plus 1. I could look at it as follows. I could choose the 1 item of broccoli, which happens choose one way. And now how many items of chocolate do I have to choose so that I have k plus 1 items total?
Okay.
I would have to choose k. Or I don't choose the broccoli, and now I have to choose k plus 1 items. And so really what's going on is we have a 1 choose 1 over here, and we have a 1 choose 0 over here. What do those numbers equal?
1.
They just equal 1. So, why would we bother writing them down? Well, it's worth writing them down to give us a sense of what's going on and to have the right dimension. When you're doing combinatorics, anything you can do to build intuition is valuable. Proof by story is one of my favorite methods of proof. I will do just one more story. Does anybody know what this sum is? The sum k goes from 0 to n of n choose k squared. Okay. So it's good that nobody is immediately shouting out the answer. Does anybody know another way of writing n choose k? How else could you write n choose k?
And choose n minus k.
N choose n minus k. So if you look, like the Dr. Seuss book, The Sneetches, there are two types of Sneetches, those that have stars on their bellies and those that don't. And eventually everyone learns it doesn't matter if you have a star on your belly or not. But if you look at it as there are k ways to choose who of the n get a star, that's the same as saying there's n minus k, n choose n minus k ways of choosing which n minus k people to exclude. Okay, so imagine we have n professors and n students. Okay, and we want a group of n people. Okay, how can we do that? If we have k professors, how many students must we have?
N minus k.
N minus k.
N minus k students. So the answer is it's the sum, k goes from 0 to n, of n choose k, n choose n minus k, which is just the sum, k goes from 0 to n, of n choose k squared. But how many ways are there to choose? We have n professors, n students, and we want a group of n people. How many ways are there to choose a group of n people?
2n choose n.
2n choose n. And there's the answer. Proof by story. Now, whenever you see this, you should always be thinking generalize. Do we study the sum of n choose k cubed or something else? And so I will leave that as something to ponder. But so much of combinatorics is about finding the right way to look at something, and that is not easy. Going back to this over here, when we did the trick, when we did this change of variables, we were able to then immediately appeal to Iwaniec-luo-Samak and solve the problem, but it wasn't immediately clear that it agreed with random matrix theory. And the student I was talking about earlier, Peng Gao from Michigan, in his thesis, he was looking at the n-level densities of certain families of Dirichlet L functions. And what he was able to do was he was able to calculate the number theory. And for n up to 3, he was able to show agreement with random matrix theory in the range in which he computed the number theory. For n greater than 3, he had the number theory, and someone else, Sonic student Rubinstein, had already calculated the random matrix theory, but we didn't know that they were the same. And in some sense, this was the most frustrating thesis I'd seen, where both sides were computed, and we believe both sides are correct, but it was not clear that they were the same. And it was a lot of work to show that they were the same. So let me just pause for 1 second. I'm going to load up the best defense, I think, in the history of Williams College, at least for the beginning talk. Are people able to see Jake Levinson's slide?
No.
Is that a yes or a no?
I think we still see the 3-level density thing.
Okay. This is annoying. So even though I'm still using the PDF viewer, I have to log out and log back on. Okay. Do you see Jake Levinson's?
Yeah.
Okay. And is it still recording?
Yeah.
Okay. So I think this is the best start of a thesis defense. So what he wanted to do was he wanted to look at the 4-level density. And so you get terms like this. And he wanted to show that that equaled an expansion like this. So I hope this gives you some appreciation for the challenge of, just because we have things computed, it doesn't mean it's easy to see that they're the same. So what did Jake do? He came up with a new way to count terms. And so what he did is he expanded. So this is the expansion of the first slide, okay? So I'm showing you the expansion. I'm still showing you the expansion. Does this look right to everybody? Equals, and then this is the expansion of the other side. And so he did this beautifully. He really sold this when he was presenting his thesis. And it's just, how do you show all these terms are the same? And he wrote some great mathematical programs to match off different terms. Okay, and for those of you who are Spaceball fans, if this works for the 4-level, what is the next question?
5-level?
5-level. And given how bad this was for the 4-level, what do you think is going to happen for the 5-level?
Be awful.
Yes. Now, do you think it'll be awful or exponentially awful? Or maybe even super exponentially awful? How bad is it going to grow? How fast do you keep getting more and more terms? And so sometimes you can brute force things. And if the result is sufficiently important, we'll do that. And at some point, I will give you my lecture on Morley's theorem as an example of how brute force can solve the problems, but sometimes you really want to search for another way. We need to find a better way. We need to find a good way to tell a combinatorial story. And Jake was able to find a better way, and he was able to prove up to, I think, the 7-level density and show agreement. And then he was able to reduce the general case to needing one identity, a combinatorial Fourier transform identity, which we weren't able to prove. But modulo that, he had the general case. And then Zev Rudnick and some of his students were able to prove the general case by using a very ingenious argument. But this is one of the most frustrating parts of the story, is to have things computed and not to know that they're the same. We talked about, I think, Green's theorem when we did the very first lecture on complex analysis. And your Green's theorem can be phrased as, this double integral is the same as this single integral. They look very different, but they turn out to be the same. And that's going to be the nature of this project, is to try to figure out, are the terms the same? The answer is yes. And just to prove why they are the same. And again, we have a great amount of it that's already done. I'm trying to keep it manageable as to what we're doing over the summer before small officially starts. There is the possibility of not wussing out and using the Iwaniec-luo-Samak result and just trying to do the 2-level calculation directly. We have 16 students in this small program. When you look at how many people we actually have the capability of dividing and trying lots of different things. In terms of writing up a paper, anybody who works on the project is an author. So everybody is an author. And sometimes the most valuable contribution is to show that a certain path is not worth investigating, that another path is better. A lot of times people don't bother trying something because they think, oh, there's no way this could work. And then later on, very foolishly, it's like, oh, all we had to do was. And so maybe we're being too clever. Hopefully, this is something that could be resolved very quickly. All right, so I think this gives a good sense of where we're going. There's a lot of things that we covered today, as always. The biggest takeaway is that if you have good averaging formulas, so the explicit formula relates what you want to study to what you can study. And then if you have a good averaging formula, then you can replace the average of the quantities that you want to study with something that's tractable. And that's the goal, is to replace these sums over modular forms with simpler things so you don't need to know advanced modular form theory. And so in terms of how much do you need to study, how much do you need to prepare, the hope is not a tremendous amount. All right, if there are any quick questions, I'm happy to answer before I run back to dealing with administrative help.
I had a quick question actually about the paper that we're intending to extend. Is that something that when we get there, we'll have to read in entirety, or are there like certain parts that we should look at like we did for ILS?
Oops, give me just 1 second.
Okay.